Imagine how a security camera works. It doesn't wait for an event, it doesn't sit idle, and it doesn't ask for permission. It simply watches, constantly, relentlessly, so that the instant something happens, it's recorded. Now take that idea and scale it up to the size of the universe. A system that never sleeps, never looks away, and never stops scanning. No operator, no manual aiming, just a machine that sweeps the whole sky over and over again, always ready for whatever shows up next. Every few seconds, it snaps a fresh image. Every few nights, it has already re-examined most of the sky and starts the cycle again. And during just its first few hours of testing, it uncovered more than 2,000 previously unknown asteroids, objects speeding through space that humanity had completely missed. Some were distant, some flew by relatively close, some moved fast. But all of them had gone undetected until this new system looked their way. It doesn't zoom in, it doesn't wait for commands, it's simply watching, because out in space, nothing announces itself before it arrives. And for the first time, we're no longer blind. Most people picture telescopes as slow, deliberate tools. You aim them at a tiny slice of sky, wait patiently, and hope something interesting falls into view. Maybe you catch a rare event, or maybe you spend the night staring at nothing. For centuries, that's how astronomy worked. Little windows into the cosmos, one small patch at a time. But the Rubin Observatory breaks that tradition completely. It isn't designed to sit still and observe one thing. It's built to repeatedly watch everything. To understand how you build a machine like that, you first have to let go of the traditional image of a telescope. Rubin isn't a long tube with an astronomer squinting through the end. It's an entirely new kind of scientific engine. Its formal name is the Samani Survey Telescope, the primary telescope of the Vera C. Rubin Observatory, a next-generation project created to transform our understanding of the universe with the most comprehensive, high-resolution sky survey ever attempted. The observatory's development spans more than 30 years. It's backed by the U.S. National Science Foundation, the Department of Energy, and research partners around the globe. Its purpose is clear: to carry out the Legacy Survey of Space and Time, a decade-long campaign that will repeatedly image the entire southern sky. The result will be a database containing billions of celestial objects, galaxies, stars, asteroids, and more, fueling breakthroughs in cosmology, planetary defense, and the study of the Milky Way. Construction began in 2015 on Cerro Pachón in Chile, nearly 9,000 feet above sea level, where thin air and consistently clear nights create ideal observing conditions. But it's not just the location that matters, it's the engineering. At the center of Rubin is an enormous 8.4-meter primary mirror, larger than the one on Hubble. Yet size alone isn't what makes it special. Rubin uses a rare 3-mirror anastigmatic design involving primary, secondary, and tertiary mirrors working together. Most telescopes rely on a single mirror and end up with a narrow field of view. Rubin's triple mirror system produces a huge, perfectly flat viewing area about 9.6 square degrees, wide enough to fit around 45 full moons in one shot. This is crucial for covering the sky rapidly. And then comes the camera, the largest digital camera ever built. A 3.2 gigapixel sensor array the size of a car's steering wheel, made from 189 CCD sensors seamlessly joined into a single focal plane. The camera weighs more than 3 tons and required engineers to create an entirely new cryogenic cooling system just to keep it functional. So why make a camera this massive if it's just scanning the sky repeatedly? Why not take small, targeted images like other observatories? Because Rubin isn't trying to study what we already know. Its mission is to capture what we've been missing. Rubin can capture a complete frame in 30 seconds, shift slightly, take another, and continue like this all night. With 6 different filters ranging from optical to near-infrared, it gathers tens of terabytes of data every night. This telescope isn't something astronomers line up to use. It's fully automated, pre-programmed to scan, record, and repeat without pause. The data flows into a massive processing pipeline where software cleans it, aligns it, and checks for changes. Something moved? Something brightened? Something flashed? The system flags it instantly. Artificial intelligence does the heavy lifting, identifying subtle differences among billions of objects and sending alerts to telescopes around the world in real time. No humans required. And here's the staggering part. In its first year alone, Rubin will gather more data than every other ground-based telescope combined has collected in decades. Think of it like this. Hubble captures breathtaking images, but it sees only a tiny sliver of the sky at a time. Rubin sacrifices zoom for coverage. Instead of focusing on one galaxy, it captures tens of thousands in a single frame, and then returns again and again to watch how they change. Over 10 years, it won't just observe the universe, it will create a cosmic time-lapse of unprecedented scale. That matters because we've missed a lot. Countless supernovae that exploded unnoticed, comets that slipped past, asteroids that approached undetected. Rubin is built specifically to eliminate these blind spots. While the world hears about a discovery, Rubin's camera will probably have recorded it days earlier. Recently, the observatory reached a major milestone, first light, the moment a telescope takes its first real images of the sky. Rubin wasted no time. Within about 10 hours, it generated over 1,000 exposures and detected more than 2,100 previously unknown asteroids. Most were harmless chunks of rock in the main belt. Some were near-Earth objects, which understandably get more attention. But the important thing is that all of them had been out there, unseen, until Rubin spotted them. One of its early images captured the Virgo cluster, an enormous region containing thousands of galaxies, about 55 million light-years away. Another early result was a detailed composite of the Trifid and Lagoon nebulae, stitched from hundreds of short exposures, showing shock fronts and star-forming regions in vivid detail. But these images aren't the goal. They're demonstrations of what the instrument can do. The real science begins when Rubin takes the same regions over and over, tracking every change. Earth still has a very real vulnerability. For all our satellites and observatories, humanity has only cataloged about 40% of potentially hazardous near-Earth objects. In 2013, a 20-meter asteroid exploded over Chelyabinsk with the power of 500 kilotons of TNT, 30 times Hiroshima, and no one saw it coming. It approached from the direction of the sun, completely invisible to the instruments watching the night sky. Rubin helps close that gap. In just 10 hours, it found more than 2,000 unknown asteroids. Over the next decade, it's expected to discover millions of objects across the solar system, from main belt asteroids to distant comets and strange objects in eccentric or inclined orbits. Early detection is everything. Spot an impactor 2 days before arrival, and nothing can be done. Spot it 10 years early, and you have time to refine its orbit, prepare a deflection mission, or evacuate threatened regions. Rubin gives us that lead time and shares its data instantly with the global astronomical community. The observatory is named after Vera Rubin, a pioneering astronomer whose work in the 1970s provided the clearest evidence for dark matter, By measuring how stars rotated around galaxies, she revealed that galaxies weren't behaving according to the expected laws of gravity, unless something invisible, something massive, was present. Her calm, persistent, data-driven work laid the foundation for the modern understanding of dark matter, even though she never received a Nobel Prize for it. Naming the observatory after her isn't just an honor, it's a continuation of her legacy. One of Rubin Observatory's central goals is to map the distribution of dark matter using gravitational lensing, the bending of light by massive objects. When the light from a distant galaxy travels past an unseen mass, its shape gets subtly distorted. Rubin's enormous field of view and sharp imaging allow it to detect these tiny distortions across billions of galaxies, creating the most detailed dark matter maps ever made. These maps will also help test models of dark energy, the mysterious force accelerating the expansion of the universe. And all this is just the beginning. Over the next 10 years, Rubin will repeatedly image the entire southern sky. Every star, every galaxy, every variable object, every event, explosions, flares, movements, transits, tens of billions of objects recorded thousands of times. It will create a searchable, rewindable history of the cosmos. Even more groundbreaking, Rubin's data will be public. Anyone with an internet connection, students, amateurs, independent researchers, will be able to analyze full-resolution images, track asteroids, hunt for anomalies, or even discover something entirely new. And because the data volume is enormous, AI systems will play a major role in finding patterns humans might overlook. Rubin might help us map the Milky Way's outer halo, catch rare transient events, or even reveal the long-hypothesized Planet 9 lurking in the far reaches of the solar system. In the past, astronomy depended on luck, being pointed at the right place at the right time. Rubin removes luck from the equation. If something happens in the southern sky, Rubin will see it, and it will see it again and again and again. The universe has always been changing. For the first time, we finally have the tools to watch it happen in real time.